All right, so in part B of number one, we are told that 1.7% of the present solar luminosity is generated by the CNO cycle. Namely, the other 98.3% is being produced by the PP chain, which is why we say that the sun is PP chain dominated. Estimate how much this would change if the central temperature of the sun were increased by a mere 1%. And our hint is to try using ratios and proportionalities instead of equations and exact calculations because the key word in this problem is estimates. So we're going to be making some approximations here. Firstly, that the sun is PP chain dominated in its present state. And then we're going to actually see later on that the sun is still going to be PP chain dominated, even if we increase its temperature by 1%. But we will be able to show that later on and not really have to worry about it right now. So we have these long analytical forms for the luminosity generation rate, or rather energy generation rate per unit mass for both the CNO cycle and the PP chain. So I'm just going to start writing them down. So we have a little coefficient out in front here, 4.4 times 10 to the 25th ergs per second per gram. So first thing to notice is that epsilon has units of luminosity per unit mass, kind of a funny quantity, but that translates to ergs per second per gram. And the reason why these constants out front already have units attached to them is because they're assuming that you will plug in numbers into the rest of the equation in CGS units. It's really, really important. In practical terms, all that means is that you need to put in the density rho in units of grams per cubic centimeter in order to get the correct number that comes out of it. You can't use kilograms per cubic meter. So just keep that in mind. Capital X is the hydrogen mass fraction of the star. So it's a dimensionless quantity. It's for something like the sun, it's going to be like about 70, 80%. Z is the mass fraction of metals. That's going to be low. It's going to be like 2% or less. And this is important for the CNO cycle because the CNO cycle depends on some metals, depends on carbon, nitrogen, oxygen, because as catalysts, it wouldn't be able to run if those elements were not present. So it's supposed to be a minus sign. That is not 3.38, that's negative 15.2. And then we have a T9 on the bottom. T9 is a dimensionless expression of temperature in units of billions of Kelvin. So just to be clear, T9 is defined as the temperature of the star divided by 10 to the 9th Kelvin. So for example, the present temperature of the sun, which we're going to use in a moment, is 15 million Kelvin, maybe we won't write this out, 15 million Kelvin or 1.5 times 10 to the 7th Kelvin. So the T9 of the sun would be 0.015. No units attached to it because the Kelvins cancel. Okay. Let me get started on writing out the PP chain numbers. It's going to look very, very similar. There's no Z because the PP chain doesn't care how many metals are in the star. But instead, it's going to have two factors of hydrogen mass fraction because there are certain steps in the PP chain where we're just slamming protons together. And just for a quick discussion on the reason why more massive stars our CNO cycle dominated is really because of this exponential terms on the right-hand side, and namely the number that goes into them. The fact that there's a really, really big number, the 15.2 in the CNO cycle versus the 3.38 in the PP1 chain, tells us that the CNO cycle as a process is a lot more temperature sensitive than the PP chain. So that's why more massive stars that are hotter are able to do the CNO cycle a lot more efficiently. Okay, so what we're doing here is dividing the CNO energy production rate per unit mass by that of the PP chain. So let's go ahead and cancel out terms that appear on both the top and the bottom. So the rows will cancel out, one factor of X will cancel out on the top and the bottom, and the units in the constants will also cancel out. And then just as a reminder, I'm using some EXP notation. It's literally just the same thing as e to the x power. I'm using this notation because it simplifies things when, or makes it easier to read when exponents get kind of crazy, which they are going to do in this problem. So when we divide those constants, we get 1.83 times 10 to the 21. We're just left over with one factor of metallicity mass fraction, one factor of hydrogen mass fraction. So remember, when we divide one number in exponential notation by the other, and if they have the same base, that means we subtract the exponents. So we're subtracting a negative number, so it's the same thing as adding that number. It's 3.38. T9 to the 1/3 power. Just gonna copy over the stuff on the left. And just add those numbers together to get negative 11.82. Because they're both, sorry, it should be T9 to the 1/3 power. And then this is where I'm going to turn this into a proportionality, because we're just interested in by how much we're changing by in what we'll define to be an initial state versus a final state in a second. So, oh, sorry, that's supposed to be proportional to. So the constants are going to drop out when we turn this equation into a proportionality. And we're just left over with dependence on T9. Oh, sorry, one thing that I forgot. Our T9 to the 2/3 power on the denominator also cancels out. Yep. Right. Great. So let's actually start a new slide because I'm have a lot more to write and I'm running out of space. So remember what we had on the previous slide, but now we're going to define an initial state versus a final state. So we have the ratio of the strength of CNO cycle to PP chain in a final state divided by the efficiency or the rates of CNO cycle to PP1 chain in the initial state. So I'm going to turn this proportionality into a ratio. Remember, our initial state is the actual temperature of the sun today, and then the quote final state would be what would happen if we increased the sun's core temperature by 1%. So these temperatures are still going to be T9s, but I'm going to suppress the 9 just so that the subscripts don't get crazy. So they're going to be TF and TI, but they're both still dimensionless expressions of temperature in units per billion Kelvin. The 11.2 is the same for both of them. And remember, when we divide two numbers in exponential notation, that means we subtract one from the other. We subtract a negative number, we get a plus. Um, just gonna simplify. Right, so we already said earlier that the core temperature of the sun today is 15 million Kelvin. So it's expressed in T9, that would be 0.015. If we take the final temperature, if we want to do the final temperature, we increase it by 1%, then that's going to be 15.15 million Kelvin, or expressed in T9, 0.01515, and that's just a dimensionless number. Subtract off the current temperature of the sun, and that's just 0.015 when expressed in T9 units. Don't forget to close all of our parentheses. Plug that into a calculator, and then hopefully you get the same thing as me. But this tells us that this ratio is equal to 1.17, or that the relative strength of the CNO cycle compared to the PP chain increases by 17%, which is a big number considering that we only increased the core temperature of the sun by 1%. And then remember at the beginning of the problem, I told you we would show that, even though this is a big jump, the star is still PP chain dominated. So we're told that the star begins as having 1.7% of its energy created by the CNO cycle. If we increased that by 17%, we would only get 2%. So we can safely say that the star is still PP chain dominated. So it's fair to say that there is a 17% increase in the efficiency of the CNO cycle as a result of increasing its temperature by 1%. And then let's quickly attach, this is number one, let's quickly attach part C since it's pretty short. Part C is asking us why are higher temperatures required for the CNO cycle to operate than for the PP chain. Well, as we saw in part A, there are interactions required in the CNO cycle that require fusion of heavier nuclei than what happens in the PP chain. Namely, we need to sometimes fuse protons with carbon, nitrogen, oxygen, which have higher nuclear charges in their nuclei than just a hydrogen nucleus. So carbon would have a nuclear charge of 6 plus 6. Nitrogen 7 and oxygen 8. So the Coulomb repulsion is a lot stronger for these reactions. And therefore, we are going to need higher relative velocities and therefore higher temperatures. These particles are going to be moving faster. So that's why we need higher temperatures. And I'll just finish writing that. Stronger Coulomb repulsion. So that's not how you spell 4. Carbon, nitrogen, oxygen. So therefore, we need higher relative velocities and therefore also higher temperatures, because that's what's going to increase the velocity. Okay, sorry, I don't like how I wrote that P. Temperature required. Right, and that concludes number 1.